Hello, good morning everybody. So we'll just continue once again with the halogens and the different halogen based compounds which are industrially important. And after fluorine we were with the chlorine and the chlorine based compounds. So what we have seen earlier, that how we can get chlorine out of the natural resources, because all these cases whatever we are discussing is based on the huge amount of natural resources, particularly the seawater what we are now looking at, where you can have the huge source of NaCl and the other halides. So after chlorine, getting the chlorine itself, that means the Cl2 molecule itself, now we can see how we can use like your sulfuric acid or nitric acid. One more important mineral acid, as we know, is your hydrochloric acid and the corresponding hydrogen chloride, which can be considered as the hydrogen chloride gas. So how we can produce very efficiently these two species, because these two are very important compounds. If we have the corresponding aqueous solution of hydrochloric acid, concentrated solution, and the dilute or 1:1 hydrochloric acid solution, starting from the laboratory use to the industrial processing and the utilization. Similarly, the HCl gas also, sometimes it is also very much useful, that if we can do some reactions or some conversions or some process development or the process making thing by utilization of the simple hydrogen chloride gas itself. So how we can get these two? So it's a very simple reaction, is a very simple exothermic reaction which generates heat from the reaction medium. Is the combination of two gaseous thing, one is the hydrogen and that is the chlorine. So combination of these two gases, as we have already seen earlier, the processing of water molecules, that means the huge source of water. Now we are considering the source of chlorine from sodium chloride or the brine water or the sea water. So we get chlorine from there, as well as we have the regular supply of water, and water, as we have seen, that one of the processes of getting hydrogen gas from water is your typical the electrolytic process or the electrolysis. So if we can have some ancillary industrial processes which can supply in a regular basis that both these two gaseous components, one is H2 and another is Cl2. So we will be able to combine them. So the reaction, as on the pen and paper case, that we can write it down like this. So is feasible also, and the amount of heat liberated from the reaction is also is corresponding exothermicity of the reaction, it also tells. So when we require basically, particularly the pure hydrogen chloride or the hydrochloric acid gas, because the purity is always very important. As we all know, the different grades of materials we know, and starting from the typical laboratory grade reagent, the LR type of reagents, to the guaranteed reagents or the analytical reagents we know, that is also a very expensive procedures for getting the higher purity of the material. So if we can have some arrangement where in-house we can make the corresponding hydrochloric acid or the hydrogen chloride gas itself, if we are going to use that particular material in the food sector, so you should be very much careful that it should not be contaminated with any other thing. So is best way of getting this is that either in situ or some arrangement for the combination of these two gaseous components, is that you make highest possible purity which can be directly used for the food industry. So if we want to use it in the food sector, so this is the corresponding procedure where we can utilize it for the production of your hydrochloric acid. So what we can have, as we all the cases we know, that whatever molecule, the new molecule or the new species we are producing or the new material we are making, we have to go for a particular synthetic procedure. So we do the synthesis, and since the reaction, as we know, that is the corresponding amount of energy per mole is liberating, as written in the reaction or the chemical equation, is the 184 kilojoule per mole what is being liberated. So that will basically heat up also the arrangement, since the exothermic nature of this particular reaction. So the furnace what will be used for this particular synthesis should have a cooling arrangement. So it can have a adjacent cooler which can be constructed out of some very tough material which is still and which is not being corroded by the starting material as well as the product of this particular reaction. That means chlorine, we all know, is the very corrosive material or the corrosive gas which can corrode iron or any other soft material which is not hard enough or inert enough. But if we can go for a particular steel furnace, it will not be able to react with that particular steel surface, and it is basically inactive with the chlorine gas as well as the corresponding material what is being produced over there, the corresponding HCl, or in the form of its aqueous form when it is getting moisture, that means the moistened one, or through some absorption tower of water like that of your making of sulfuric acid when sulfur trioxide is getting absorbed in absorption tower of water. Similarly, this particular case also the produced hydrogen chloride gas can absorb water and produce us the corresponding aqueous solution of hydrochloric acid. Depending upon its corresponding concentration of the gas and the amount of absorption, we get the different varieties or different concentrated solutions of this. So we have to have the dry HCl and the dry hydrogen gases because it should not be moistened. That means the production of this reaction, that means the combination of these two gases which is producing us the corresponding HCl, and that HCl should also be dry. Because sometimes we have, if we have some doubt in it that the gas produced over there has some moisture, we should try to avoid that moisture also. So we must have some drying column or the moisture trap in between from the outgoing gas what is leaving the furnace, that synthesis furnace. You should pass through the different columns which can absorb the moisture and which can take out that particular amount of moisture from all these cases, and the corresponding reactions stoichiometry will also tell us that the produced HCl should not have the starting material, or that means these two initial gases what we are using for these reactions, that means it should not have the H2 as well as Cl2 in it. So the amount what is being produced, so we should have also not only the trap for the moisture or the water vapor in it, if sometime it can come. You can also some trap for the unreacted Cl2 or unreacted H2 which can also be going out along with the hydrogen chloride gas which is being produced from this reaction. So sometimes it is also obtained as a byproduct. So if we consider that any kind of reaction, we all know that if we are able to remove some chloride from some organic molecule or some other group, that means the CCl bond is being broken or being reduced with that of your hydrogen gas or hydrogen on some catalytic surface like that of your palladium charcoal or anything. So one of the product for that particular reaction is your typical HCl. Similarly, it can be a byproduct for different other chlorination reaction or the halogen reactions in organic chemistry. So what are those examples? Basically what we can have in our hand where we get HCl as the byproduct. So if we are concentrating our attention for the material, that is the target molecule what we are making through this particular organic transformation like that of your simple chlorination or the chlorine exchange reactions, we should also take care of the thing, because if the HCl produced is in the gaseous form, so we should take out that means over the reaction medium, if the other material, if it is pharmaceutically important or it is a dye molecule, so over the reaction medium we should have the gas molecules which is covering the reaction medium, the liquid reaction medium. So we should have the corresponding exit pathway above the liquid such that we can take out the byproduct as HCl from that particular outlet. So we should have the typical provision of making that particular outlet which can take out the HCl which is being produced from there as a byproduct of any kind of reaction. So first of this category which can be considered as a typical example for this byproduct chemistry or the byproduct isolation as HCl is the manufacture of aliphatic and aromatic chlorohydrocarbons. So if we can go for chlorohydrocarbons, that means we know that hydrocarbons are CnH2n plus 2 type of thing. That is, we can have carbon as well as some hydrogen atoms attached to that particular carbon center. Then if we are able to substitute, that means some of this CH group or the CH functions can be substituted by CCl function. That is, if we have the methane which is CH4, if we substitute only one of the CH bond of the methane by CCl, we get that is the chloromethane or methyl chloride. So during that particular procedure of making the methyl chloride out of methane, because methane we know is a availability is plenty starting from your natural resources like that is of your natural gases. So if we are able to make it from that particular case, that if we are able to make this particular reaction with chlorine, so chlorine will react with that particular one as your corresponding chlorination of the molecule, as well as it will take out that hydrogen as H plus, and chlorine will give you the Cl minus, producing your HCl. So that way you can justify also the production of HCl from that particular reaction. So if we have a corresponding chlorination reaction for hydrocarbons in industrial scale, so huge amount of that material we are trying to produce, and that particular case we should not ignore the production of HCl, because HCl is a gas. It can come out from the reaction medium, the reactor medium or the reactor, huge reactor. So the gas will just come, and if we are not able to take care of that particular gas, which is basically a valuable product, valuable byproduct from the reaction medium, if we are not able to track that particular one, we will just simply throw away into the environment. So it will just pollute the environment. So there should be a very serious environmental concern out of that. So if we are very much capable of tracking that particular amount of production of HCl from that byproduct reaction, we should be able to trap the entire amount of HCl what is being produced from that particular reaction. So there is no need to produce separately HCl for some other industry or for the same industry where we are going for the chlorination reaction, but we can have some arrangement such that we can trap the product of HCl. Similarly, during the manufacture of isocyanates, we all know that the typical organic isocyanates, the SCN group, having the SCN group, by reacting amine with phosgene. So it's a very simple reaction where we get the cyanates. Cyanates is nothing but either a functional group of CNO or OCN. That OCN part what is being attached to the alkyl function R, we get the isocyanates. How we get that? We start from the amine, that means it is a molecule having the amine function, NH2 function attached to the carbon and the hydrogen based molecule. So on that we are trying to put C and O such that you get a function or the functional group which is utilized for the conversion of your NH2 to NCO, such that you get the corresponding isocyanate molecule out directly from the amine itself. The most reactive species for that particular one is your phosgene. Phosgene is also a gas which is COCl2, nothing but you have the CO, the carbonyl function like your carbon monoxide, and that carbon is attached to two other Cl functions. So when it reacts with the phosgene reactivity thing, the reaction is such a giving you that particular reaction that it is only reacting with the amine function, and that amine function is also giving out two of its hydrogen from NH2, it is the primary amine one. So the primary amine function having a NH terminal NH2 group is giving two of these hydrogen atoms to the phosgene molecule and taking up the CO part of the phosgene molecule inside it, making that N to NCO, that means the alkyl or the other type of substituted isocyanates, and by that time it is producing the double amount of H plus Cl combined thing, that means the hydrogen chloride. That means double of this it can produce, because we do not need any catch of chlorination reaction where chlorine is being inserted into the molecule itself, but here we are taking away all the chlorine from the phosgene molecule such that taking the hydrogen atoms from the amine function, it will produce double amount of HCl. So now HCl in a greater amount is again a byproduct for the reaction, and we should take care of that particular product, and we can store it, we can purify it, and we can preserve it for further use. Similarly, manufacture of another pyrogenic silica is a special variety of silica, pyrogenic, which is heat sensitive also, by flame hydrolysis of chlorosilane. We all know that is the chlorosilane, SiH4 is the silicon hydride, where all the 4 hydrogen atoms are attached to the silicon, and if one of them, like your methyl chloride or chloromethane, now carbon can be replaced by silicon only, so it will be SH3Cl, like your CH3Cl. So chlorosilanes can also be treated for producing silica itself, that means the silica as in the elemental form. So when it is producing in the elemental form, and the chlorosilane itself has different varieties of chlorosilane we can have. You can have 1 chlorine attached to the silicon, 2 chlorine can be attached to the silicon center, or 3 chlorine centers can be attached to the silicon center. So during that particular processing, that means the making of silica itself, that means silicon dioxide, silica, pyrogenic silica, or the silicon itself, the elemental form also, in all these cases you have to remove the corresponding hydrogen attached to the silicon center or the chlorine attached to the silicon center, and these two can combine further to produce you the hydrogen chloride once again as your byproduct molecule from the industrial scale of making this pyrogenic silica out of chlorosilanes. Hydrochloric acid utilization, if we now consider that what are the areas where we can utilize this hydrochloric acid, because why we need the manufacturing of hydrochloric acid in the industrial scale. The reaction is a very simple one, only thing that how big reactor you can use and what are the other conditions you can optimize. In terms of your chemical engineering aspects, you can also standardize all these things, but we are basically interested to know how we can utilize, because without utilization you cannot produce that much amount of hydrochloric acid or hydrogen chloride for giving you a new chemical in the industrial scale. So first of this is your cleaning of the metal surface. So if we all know that the surface, when if it is the iron surface or any other surface, most of the metal surfaces are combined with that of your corresponding oxide formation from the reaction with the air, or sometimes sulfide formation or the carbonate formation through the reaction with the carbon dioxide of the air. So all these materials basically, that means when we clean it or react with those surfaces, that means if it is a oxide surface or a hydroxide surface or the carbonate surface of the metal, we treat it with hydrochloric acid such that your hydrochloric acid will take care of the corresponding anionic part as your metal anionic form, that means the corresponding anions can be taken away, and if possible, if we are able to reduce that particular free metal ion on the surface, you can get the metal ion as the zero form, again it can come and attach or stick to the metal surface, otherwise it can be cleaned or it can be leached from the metal surface as the typical metal ion salt of the corresponding chloride ion which is available from hydrochloric acid. So if a metal surface is covered with hydroxide or the oxide or the chloride surface itself, if we can treat it with hydrochloric acid, and if the solubility of the already present carbonate surface or the chloride attached to it is also not very much, but the fresh amount of addition of hydrochloric acid will clean it as the corresponding metal salt from the surface such that we get a very shiny surface or a very clean surface, because we require most of the cases when we directly use in the industry, that we see also afterwards when we talk about the corresponding industry which is producing the high grade of metal center, high grade of silicon center, which are having a huge demand in the industry. So metal cleaning process can be utilized through the use of the product of our industry is the hydrochloric acid. Then sometime not typical cleaning, but we consider that industrially is known as the pickling. So like the pickling of the metal surfaces or the metals, all the metal material also is also done by the hydrochloric acid, and sometimes the manufacture of metal chlorides from the free metals or the metal oxides or hydroxides, carbonates or different types of ores and minerals. So, how we go for getting that particular metal as the metal salt? If the industry is only devoted to something where we do not produce the metal itself, but we are directly producing or converting the ore or mineral to your metal iron salt. That means iron, we take hematite or magnetite for the production of ferric chloride, say, or the iron sulfate or ferric nitrate. So, making these for the different types of chloride, that means the ferrous chloride or ferric chloride, we directly treat those metal or the metal oxides with that of your hydrochloric acid. Then in the typical classroom or the research level laboratories, they are using huge amount of hydrochloric acid for simple neutralization reactions. So, that neutralization reactions in any chemistry of inorganic, organic or some biological world also, the biochemistry, the bioinorganic classes or the biophysical classes, the first thing what we do, that if you have a solution and that solution also very important industrially also, when there will be some adjustment in the pH. Suppose our raw material is a simple sea water, that we will see in our next class possibly, that if we try to get the bromine out of the sea water, because the bromine concentration as bromide in sea water is very less, but for getting that particular bromide as the free bromine, we should have some reaction that we will see, but before that we have to go for the typical neutralization reaction. So, the neutralization reaction for the different types of organic and inorganic reactions, or sometimes for the bulk material, things are very simple, that how we neutralize it. When we neutralize, we are talking in terms of the corresponding neutralization, in terms of the basicity of the carbonate, the bicarbonate or the corresponding hydroxides or the oxides. When we go for the neutralization, we are taking care of the pH of the medium, but if we just try to ignore the corresponding supply of the anions out of the acid what we are using, because when you use hydrochloric acid and a huge excess of hydrochloric acid if we add to adjust the pH, to control the pH, by that time we are contaminating the reaction medium with huge amount of chloride ions which is coming out directly from the HCl. Similarly, if the medium is not good enough to sustain with that of your excess chloride, we should try with that of our other acids, other inorganic acids, other mineral acids like that of your sulfuric acid or nitric acid, if chlorides are not good enough for the particular type of reaction what we are looking for. But in most of the cases, hydrochloric acid is the preferred one, or HCl gas, passing HCl gas in the gaseous form also is the most useful one for neutralization reactions. Then proton catalyzed or acid catalyzed reactions in the biochemistry or in other areas are well known. We know that a typical reaction we always follow is the hydrolysis reaction. So, HCl is again a very good material for the hydrolysis reactions of proteins and carbohydrates. It is giving you for the corresponding idea that it can go for the lysis reaction, that means the breaking of some bonds like ester hydrolysis or any other thing, where water is basically attacking that particular bond, that means the ester bond is getting hydrolyzed to give you the acid and the alcohol back. But that particular acid, either it can be acid catalyzed or base catalyzed. So, most of the cases if it is acid catalyzed, so this hydrochloric acid or HCl is very good to go for this type of hydrolysis reaction for the proteins, the peptides, the polypeptides and the different types of carbohydrates also. Then one more important thing is that what we will also study now is the making new molecules out of this HCl. One such new molecule is like that of your chlorine oxide. If we move from chlorine to chlorine oxide for water treatment, acid treatment of oil wells and all these things. So, when we go for acid chlorine oxide, we can use it for corresponding water treatment as well as acid treatment of oil wells also, that means the adjustment of the corresponding pH of the acid wells also. And if we are not able to put directly the HCl, we will use the chlorine oxide, that means Cl2O. When we produce this HCl, and most of the time what we produce as a byproduct, and since the byproduct amount if it exceeds to a value. That means huge amount of HCl we are producing through that particular industrial activity, and what we find is that HCl produced through this particular process by that thing is the byproduct, and when it exceeds the demand, that means whatever amount of HCl we require and whatever amount of HCl we produce which exceeds the demand, then we have the excess amount. How we can consume that particular excess amount of HCl? There is no worry to make. We can only convert back again, because we know the procedure how you can convert the chloride, that means NaCl, to chlorine also. Similarly, you have again a good quality of chloride supply, that means the chloride ion supply as HCl, and that chloride ion supply will be utilized for converting back again to chlorine. So, we can have the remaining amount what is not required from HCl utilization, will convert directly it to again the chlorine gas. We can preserve it in the cylinders or any other storehouse. Then, as I told you, that we can see how we make this particular chlorine attached with some oxygen. That means we will definitely have some chlorine oxygen bond. Earlier we are making Cl2, then we are making HCl bond, and HCl bond is also very much useful for breaking and creating of the new bond. Now we are moving to some species where you can have the chlorine oxygen bond. That means how it is possible to convert the corresponding one as the oxidation of the chlorine, if we consider that attachment of the oxygen atom to the chlorine center. So, one such example, as we all know, that is the typical making of the hydrochloride, sodium hypochlorite. We can make it. How we make it? Sodium hypochlorite is nothing but the bleach we use, the common day laundry bleach, the washroom or the bathroom bleach. The common day is the bleaching agent. So, that bleaching agent is nothing but NaOCl. As we know, the bleaching powder, the name is also, because nowadays we don't use that much bleaching powder, because in the acidic medium or the aqueous medium it is producing free chlorine, and free chlorine is always harmful for our health or body, and is also harmful for the environment. So, a dilute solution of hypochlorite, instead of using calcium OCl, CaOCl, Cl, we can use sodium hypochlorite, NaOCl only. So, there is no chance of getting free chlorine out of this. So, we have this. How we make it? So, the second reaction is the production of your bleaching powder. We just simply compare side by side how we can get this of making hypochlorite from calcium hydroxide. So, we get the calcium hydroxide, react with the chlorine at room temperature, mostly is the room temperature reaction, giving you bleaching powder per water. Similarly, if we pass chlorine gas, that is why when we produce chlorine and you can get that chlorine and the supply of that particular chlorine gas, you can pass it to a saturated solution of sodium hydroxide, a sufficiently concentrated sodium hydroxide solution, giving you both NaOCl and NaCl plus water. And the same reaction when you have the bivalent cation, such as that of your calcium, which is a bivalent cation, and this particular reaction is nothing but base assisted disproportionation reaction between the formation of chloride as well as the hypochlorite ions. So, making of these chloride and hypochlorite ions through this disproportionation reaction in basic medium, we are producing two anions. So, when we have mono cation, that is sodium ion, the sodium ion will take care of both these two anions, producing NaCl as well as NaOCl. But when you have the bivalent cation, that means calcium hydroxide is there. So, already you have calcium bound to hydroxide groups, and if we can able to convert one of them as OCl and another as the Cl, which is being applied to it, so we get the calcium having that both these two chloride and hypochlorite ions attached to this particular calcium center. So, the problem is that when we add it in the acidic medium, again the hypochlorite and chloride will combine in presence of free or excess protons at the H plus, producing water as well as the chlorine and the calcium hydroxide from there. So, we can avoid that particular thing if we can separate these two things, because if we can produce sodium hypochlorite and sodium chloride together, what we will find that these two together can have the fractional crystallization itself. That means if they can have the different solubility, and that solubility difference will tell us where we can go for crystallization of sodium chloride and where we can go for the crystallization of sodium hypochlorite. So, separate crystallization, what we call the fractional crystallization process, only giving you the production of sodium chloride. Half of the molecules will be the sodium chloride production as well as the sodium hypochlorite solution. This way we will be making a huge amount of sodium hypochlorite solution, because the sodium hydroxide is also a very cheap material, and if we are able to get chlorine out of the seawater and all other sources, we can get sodium hypochlorite also. So, in our next class we will be considering how these hypochlorites or these bleaching agents are also useful and other chlorine oxygen compounds. Okay, thank you very much.